Okay, so we're going to continue 4.1. So yesterday we talked about the extreme value theorem. And so some of the things that we had to have a continuous function on a closed interval. And so here were some of the examples that we did. So we had to find the critical points. And the critical points are where the derivative is equal to 0 or where it's undefined. So this one we set it equal to 0. It's not undefined. We've got a critical point of x equals 2. And then I said, okay, so we have to test the endpoints and the critical points. The largest value we get is the absolute maximum. The smallest is the absolute min. The second example, we did the same thing. We did the derivative. However, the derivative is not going to be equal to 0. However, it's undefined when x equals 0, so that's our critical point. So we tested the critical point and the endpoints. Same thing, absolute min, we got to be 0, and absolute max, cube root of 9. And then the last example that we did the derivative. We got no critical points, so we were only testing the endpoints, and so we got the absolute max was here, absolute min here. So what we want to do next is consider what about local extreme values, also known as relative extreme values. So here we have a number of different, here's a maximum, right? Here's a minimum, here's another maximum, and then we also have the endpoints. So this is a minimum, and this is a minimum because it starts and it goes up. Okay, so we know about the absolute maximums. So we have a way to test that from the beginning, from yesterday's lesson. And then here's the absolute minimum. So remember how I said it's where the derivative, this here, f prime, if you can kind of see that this is undefined right here. And then this is an endpoint. So remember we talked about that you could have extreme values where the derivative is equal to 0 or where it's undefined, or at the endpoints. So local maximums and minimums are very much the same. They can occur. This situation here, we get the derivatives equal to 0. This one here, f prime is equal to 0. And this one here is an endpoint. Okay, so this is like what we talked about yesterday again. You have a local maximum if and only if all the values are smaller than our particular point on some open interval, and then local minimum if all our values are above, greater than or equal to one particular point. So a function has a local maximum or minimum value at an interior point if f prime exists, then we know it has to be equal to 0. Now our steps here, this is going to be really important for the next section. So to find local extrema, and this will lead into the next section where we are going to consider where a function is increasing or decreasing. So first thing we want to do, find the domain. That's step 1. Next, we want to find the critical points, and we want to make sure that the critical points are in the domain. Again, how do we know that we have critical points? Just as a reminder, this is where f prime is equal to 0 or where f prime is undefined. Next step, we're going to create a number line for the derivative. We're going to label any critical points and any endpoints. Just a quick note, it's often also helpful to put in open circles at any points that are excluded in the domain. Using the number line, we're going to test values by plugging into f prime of x. And then we're going to label basically pluses where you get a positive, and we're going to label negatives where you get a negative value, a minus sign. So where this number line changes from plus to negative, there's a local maximum. Where it changes from negative to positive, local minimum. And then to actually find the max and min, we plug in to f of x back into the original. So I know these are a lot of steps, so it's I think what I'm going to do is I'm going to walk you through the first example, and then we'll kind of go back to the steps. Okay, so we want to find the extreme value. So when we read something like this, we're not just talking about the absolute maximum, absolute minimum. We want local maximums, local minimums. Step 1. So take a look at step 1. It says find the domain. So in this situation, notice extreme value theorem, we had a closed interval. We could have a closed interval, but in a case like this, there's nothing to say what our domain is. This is a polynomial, so we think about what can we plug in. We can plug in negative infinity to infinity. This has no endpoints, by the way. Okay, step 2. We want to find the critical points. So we're going to do the derivative. So we get 3x squared plus 3x minus 6. Now I know I'm going to solve this equal to 0. So before we do that, I'm just going to factor it out. So take out a 3, and then we can factor this out. It'll be x plus 2, x minus 1. So I want to set this equal to 0. So my critical points, okay, so I consider each part. Well, I can't set 3 equal to 0. That doesn't make sense. But if I take x plus 2, set that equal to 0, I get negative 2. And set x minus 1 equal to 0, I get x equals 1. So these are my 2 critical points. Okay, so I've completed step 1 and step 2. We found the domain. We found the critical points. We also just want to make sure, so in step 2, I said make sure that the critical points are in the domain. Our domain is from negative infinity to infinity, so we're good. Step 3, create a number line for f prime of x. So leave, I don't know, say like an inch, at least an inch of space, and then we're going to create a number line. Make sure you label it f prime. This is really important because later on we're going to do the second derivative, and I want to make sure that we keep all of our number lines straight. So I'm going to now put on my number line any critical points and any endpoints. So my critical points were negative 2 and 1. And we said there were no endpoints, so I'm just going to put here negative infinity to infinity just to kind of have a reference there. Now, I want to, so now I'm on step 4, using the number line, we're going to test values within each interval. So if I look at my number line, I have 3 separate intervals, and I want to test into f prime of x. So pick something here, say negative 3. So I'm going to plug back into the derivative over here. So I have 3, well that's positive. Plug in negative 3 here, so negative 3 plus 2 would give us a negative. And then negative 3 minus 1 would also be negative. So I have a negative times a negative is positive. So we're going to put a little plus sign. Next, pick something in between negative 2 and 1, say 0. So I go back to, again, we're plugging these in right here. So if I plug in 0, I have 3 times 2 times negative 1, so that's negative. And then pick something to the right of 1, say 2. So I have a positive times a positive times a positive. So I put a little plus sign. Now, this is the derivative. So this tells us that we have slope. If I know it's a positive slope, I know my curve is going to go up and to the right. So we draw an arrow above. Next, if my derivative is negative, I know I'm going to go down to the right. That's the way the line looks, or if you have a decreasing function. And then plus, we're going to go up to the right. Now what happens is these arrows tell us the behavior of my graph. So I know it's going to start here or it's going to go all the way down to negative infinity actually, and it's going to go up, and then it's going to be reaching the maximum value. Then it's going to go down, and then it's going to be reaching a minimum value at 1, and then it's going to go on. Now these are not absolute, because again, if you kind of imagine this goes on to infinity, this is what we'd have, a local max. So I have a local max is going to be f of -2. So you're going to plug -2 back into the original equation. That's why it has f, not f prime. And just to save time, you can plug it into your calculator and verify. We get 11. The local minimum is going to be f of 1. You plug 1 back into the original, and we get -5/2. Okay, let's do another example. So I have f of x equals 1 over x squared minus 1. Step 1, what is my domain? Okay, so my domain in this case, I can't have plus or minus 1. So I have from negative infinity to 1, union -1 to 1, union 1 to infinity. Next, we're going to do the derivative. So we can do quotient rule, or you can change this to a power. I'll do quotient rule. So I have low, d high, take high, d low, cross the line, square the low. So this is going to be 0. So I have a -2x over x squared minus 1 squared. Now when I try to set this equal to 0, that's going to be setting the numerator equal to 0. So this is where f prime equal to 0. How about f prime undefined? That would be setting the denominator equal to 0. In the first part, we get x equals 0. Here, we would get plus or minus 1. But remember how I said we want to make sure that the critical points are in the domain, and they're not. Okay, so we had, so these values were not in the domain, so that means my critical point is just x equals 0. Okay, so I'm going to make my number line. That's step 3. And we want, oops. Okay, so this is f prime. We only have one critical point at 0. However, I said that it's helpful to put open circles at any points that are excluded in the domain. So we said at -1 and at 1, we technically have open circles here because it can't be equal to that. And we don't have any endpoints, so it goes from negative infinity to infinity. We don't really need to put those in there, but just, again, as a reference. Okay, so let's take a look. Let's pick something. Now, I should get the same thing in this entire interval from negative infinity to 0. It's just that we can't plug in -1. Again, we're plugging into f prime. So we're plugging in to here. Notice the denominator is squared, so I know my denominator is always going to be positive. So we really just have to consider when we plug into the numerator. So let's say I choose -2. If I choose -2, I have -2 times -2, which is positive. Now I could plug in a -1/2 here, but you should notice that I still get positive here. Then if I plug in numbers to the right of 0, say 1/2, I get a negative. And again, if I plug in 2, I can just verify I get negatives there. So my graph is going to go up, continues going up, then it goes down, continues going down. So the only place that there was a switch is right here. which implies that there's only a local maximum, which also ends up being the absolute, just because there's no other values that go above this. There are no minimums. Okay, example 5. So we have a piecewise function. So let's consider the domain. The domain here, so it says x is less than or equal to 1, x is greater than 1. That implies that we can plug in all reals. Next, we want to find the derivative. Okay, so the derivative of the first line, we get negative 4x. When we have the derivative, we drop the equal to sign, okay, because this could imply that there would be a corner. The derivative of the second part, x plus 2 becomes 1 when x is greater than 1. So we have a couple things to consider. We want to see where is f prime equal to 0 and where is f prime undefined. Okay, so basically we look at each part. We have negative 4x, see if that can be equal to 0. The other part, 1, well, that can't be equal to 0. There's nothing to solve there. So we get x equals 0. Remember, our domain was negative infinity to infinity, so that is a critical point. The other question is, where is it undefined? So when do we not have a derivative? Well, we don't have a derivative when there's a discontinuity, but we can verify if we plug in that is continuous. The other options are corner, cusp, or vertical tangent. Well, this is clearly not a cusp or a vertical tangent. So we have to consider, is this a corner? Well, how do we tell if there's a corner? Well, if you plug in the values for the derivative, right? So, for example, if I look at the derivative of 1 from the left, I get negative 4. If I look at the derivative of 1 from the right, I get 1. This implies, since these are not equal, they have different slopes from the left and right, that's a corner. So we have another critical point at x equals 1, because that's where it switches. That's the x value. So we're going to create a number line. This is still f prime. So we have 0 and we have 1, and it's negative infinity to infinity. So remember, I'm still plugging into right here. So the number line, I'm plugging into the derivative. So let's look at the first interval. I have from negative infinity to 0, so let's plug in negative 1. So since this is a piecewise function, I can only plug into one part. So negative 1 falls into the first line. So negative 4 times negative 1 will be positive. Next interval, between 0 and 1, let's say it's a half. Well, half also falls into that first line, so negative 4 times 1/2 is negative. Next one, I have from 1 to infinity, so I can choose 2. And actually anything bigger than 1 is going to result in a positive 1, so that's positive. So my graph goes up to the right, down to the left, up to the right. So we have a maximum here and a minimum here. Now, because this goes to negative infinity here, and it goes to positive infinity here, these are both local maximums and local minimum. So our local maximum is f of 0 equals 5. Again, how do we get that? We take the 0, but remember this is f, not f prime. We plug it back into the original. And then for our minimum, we have f of 1. Plug 1 in, so we plug that back into the original here, and we get 3. Okay, so now what I would like you to do is go ahead and work on the homework for the rest of the class, and we will go over homework questions on Tuesday when we meet again.